Data transformation is the process of converting raw data into a format that is easier for algorithms to learn from and for data scientists and data analysts to explore. It is a core part of feature engineering that helps reduce bias from skewed distributions. First, it makes features in the dataset comparable by putting them on similar scales and magnitudes, which helps models learn patterns more effectively. Secondly, it reduces skew and limits the impact of extreme outliers, which can otherwise bias your results. In this walkthrough, we'll use a marketing analytics dataset from Kaggle that contains customer demographics and purchase behaviors. We will demonstrate how to choose the appropriate data transformation technique according to the data properties. That includes domain-specific basic feature engineering. Apply log transformation for right skewed data. Clipping methods for handling outliers. We will also compare 3 data scaling techniques: MinMaxScaler, StandardScaler, RobustScaler. For an article guide of these concepts in more details, please check out blog post with link in the description. Now let's start with simple feature engineering to make the data tidier and more meaningful using the pandas library in Python. First, we convert year of birth into an age feature by subtracting it from the current year. Then we turn the customer enrollment date into an enrollment_length feature by extracting the year and computing how long each person has been a customer. Next, we clean the income column. We remove currency symbols and commas, fill missing values with 0, convert the string to an integer, and then scale it down to millions of dollars as a new feature, income_m$, which makes the distribution easier to visualize. Once we've engineered these basic features, we plot simple histograms for each numeric column. It quickly becomes clear that many variables are heavily right-skewed, and some, like age and number web visits month, contain extreme outliers. This is where transformation really matters. If we feed skewed and unscaled data directly into a model, it's more likely to become biased and misinterpret distances and relationships between points. For features that follow a power law pattern and have long right tails, we apply a log transformation using functions like np.log. In this dataset, most of the skewed variables fall into this category. After log transformation, the distributions become closer to normal distribution, which helps many algorithms that assume roughly Gaussian inputs. Next, we tackle outliers with clipping. We define upper and lower bounds using quantiles, typically from the 5th to the 95th percentile, and then cap all values outside this range. In practice, that means any values below the 5th percentile are raised to the lower bound and any values above the 95th percentile are reduced to the upper bound. For this dataset, clipping is particularly useful for age and number web visits month, which contain implausibly large values. This prevents a few extreme records from dominating the learning process. Once we've corrected skew and outliers, we scale the features so they share a comparable magnitude. For this, we rely on preprocessing tools, MinMaxScaler, StandardScaler, and RobustScaler. MinMaxScaler performs normalization, mapping each feature into a 0 to 1 range based on its minimum and maximum values. It's best used when the data isn't heavily distorted by outliers. StandardScaler does standardization, transforming features so they have mean 0 and variance 1 using the classic z-score formula. This is ideal when a feature is roughly normally distributed. RobustScaler is designed for skewed distributions and remaining outliers. Instead of mean and standard deviation, it uses the median and interquartile range, making it much less sensitive to extreme values. To compare these methods, we iterate through the numeric features, including those we clipped, and scale them using each of the 3 scalars in turn. The transformations don't change the shape of the distributions, but they do change the spread of the values. In this particular dataset, the key variables are neither severely distorted nor perfectly normal, so min-max scaling is a reasonable choice. Once all the transformations are applied, we plot the histograms again and compare them side by side. The before view shows heavily skewed, messy distributions. The after view looks more organized, with less distortion and more balanced ranges across features. This cleaner representation makes the data far more suitable for model training and for drawing insights through analytics and visualization. To recap, here's a quick checklist for numeric feature transformation. First, clean your data types and remove unnecessary characters in numeric fields. Second, apply log transformations to write skewed features. Third, use clipping to rein in outliers based on sensible quantile thresholds. And finally, choose a scaling method that fits your data: MinMaxScaler for generally undistorted data, StandardScaler for approximately normal distributions, and RobustScaler when skew and outliers are still a concern. Thanks for reaching the end. Check out links in the description for more deep dives and related contents. Please like and subscribe if you'd like more videos like this.